In this episode, we're diving into the world of color clustering and palette creation using Python. Imagine extracting the essence of an image and boiling it down to a stunning, sorted color palette. Whether you're an artist, designer, or data enthusiast, this journey into simplifying and recoloring images with machine learning will open up new creative possibilities. We'll walk through every step from clustering colors to generating a polished color palette and even recreating the image itself. Let's get started and turn pixels into pure artistry. To kick things off, we import the essential libraries for our project. First, NumPy is brought in for numerical operations, which will be useful for reshaping and manipulating the image data. We're also using matplotlib.pyplot to handle the visualization of images and color palettes. From SkimAge, we import tools for working with images, I/O for loading and displaying the image, RGB2Lab and Lab2RGB for converting between RGB and lab color spaces, which is important for accurate color clustering, RGB2HSV and HSV2RGB for sorting colors based on their hue. Finally, from sklearn.cluster, we import mini-batch k-means, a fast and efficient clustering algorithm that allows us to group the colors in the image into meaningful clusters. With these tools ready, we're set to start working with colors. Here, we define a utility function, displayImage, that simplifies the process of displaying images with customization options. This function accepts an image as input along with optional parameters for the title, figure size, and background color. Uses plt.imshow to render the image and plt.axisOff to remove axis labels for a clean display. If a title is provided, it's displayed above the image in white for contrast. Allows setting a custom background color for the figure using setFaceColor, making it ideal for presentations or themed visuals. This reusable function ensures we can consistently and cleanly display images throughout the episode. Now, let's load and display the image we'll be working with. First, we use io.imread to load the image from the specified file path, /data.johnwick.webp. This reads the image as a NumPy array, making it ready for processing. Next, we call our displayImage function to visualize the original image. By setting the title to original image, we clearly label the starting point of our project. At this stage, we have the image loaded and displayed, providing a baseline for the transformations and clustering we're about to apply. Now, we begin the process of clustering the colors in the image. First, we convert the image from the RGB color space to the lab color space using RGB2Lab. Lab is more perceptually uniform, meaning differences between colors are better represented for clustering. The image is then flattened into a 2D array where each row represents a pixel, and the 3 columns represent the lab color components. Next, we set the number of colors, nColors, to 8, defining the number of clusters we want to extract from the image. We initialize a mini-batch k-means model with nClusters equal nc, specifying the number of color groups, random state equals 0 to ensure reproducibility, ninit 10 for multiple initialization attempts to find the best result, a batch size of 256*8 for efficient clustering on large datasets. Finally, we call km.fitFlatImg to cluster the colors. The algorithm assigns each pixel to one of the 8 clusters, capturing the dominant colors in the image. This sets the stage for generating a color palette. Now, we extract the color palette from the clustering results. The km.clusterCenters attribute gives us the lab values of the 8 cluster centers. These represent the dominant colors identified by the k-means algorithm. Next, we convert these lab values back to the RGB color space using Lab2RGB. To do this, we first reshape the cluster centers into a 1xn array where each cluster's lab values are treated as a single pixel. The result is palette RGB, an array of RGB values representing the main colors in the image. This palette will be used to visualize and further process the dominant colors extracted from the image. Now let's visualize the extracted color palette. We use the displayImage function to display palette RGB, the array of RGB values representing the dominant colors in the image. By setting the title to color palette, we clearly label the visualization. This gives us concise and visually appealing representation of the main colors identified by the k-means clustering, allowing us to see the essence of the image distilled into just a few shades. Now we refine the color palette by organizing it based on hue for a more structured display. First, we convert the RGB color palette to the HSV color space using RGB to HSV. HSV, hue saturation value, allows us to sort colors more intuitively by their hue. Next, we calculate the sorted indices based on the hue values using np.argsort. This ensures that colors are ordered from red through the spectrum to violet. Using these indices, we rearrange the palette in RGB format to reflect the sorted order. Finally, we call display image to visualize the sorted palette with the title sorted color palette. This step makes the palette easier to interpret and provides a visually appealing way to understand the dominant colors in a logical order. Now we apply the clustered colors back to the image to create a simplified, recolored version. First, we use km.predict to assign each pixel in the flattened image to one of the 8 clusters identified earlier. This generates a set of labels where each pixel is associated with the closest cluster center. Next, we map these labels back to the corresponding cluster colors in the lab space using palette lab labels. The result is reshaped to match the original image dimensions. Finally, we convert the lab values back to RGB using lab2RGB to produce the recolored image. We use the display image function to visualize this clustered version with the title clustered image. This simplified image highlights the dominant colors, showing how the k-means algorithm has distilled the original image into just a few key shades. Now, let's convert the sorted color palette into a format that's easy to use and share: hex color codes. First, we scale the RGB values from their default range of 0 to 1 into the standard 0 to 255 range by multiplying by 255. We then convert these values to integers and reshape the palette into a flat list of RGB triplets. Next, we create hex color codes for each color in the palette using Python's string formatting. For each RGB triplet, we convert the values into their hexadecimal representation, prefixing them with a # Finally, we join these hex codes into a single string separated by spaces and print the result. The hex codes provide a clean, compact way to represent the dominant colors, perfect for use in design tools or web applications. Thanks for tuning in to this episode. Today, we explored the art of extracting and clustering colors from an image, creating a stunning palette, and simplifying the image into its core hues. Along the way, we learned how to visualize and sort colors and even generate hex codes for easy use in design or development projects. This process is a great blend of creativity and coding, showing how algorithms can transform visual data into something useful and beautiful. Don't forget to try it out with your own images, and I'll see you in the next episode for more exciting projects.